Welcome back, students. In today's lecture, we are going to discuss on the phase diagrams. Phase diagrams are graphical representation of what phases are present in a material system at various temperatures, pressures, and compositions. So, in the last class, we have discussed on what is a phase. A phase is nothing but it is something which is physically distinct is called as a phase. Okay, so and also we have discussed on what is a solute, what is a solvent, what is the solubility limit, what is the supersaturation solid limit, like that. Okay, so with those basic understanding we can proceed into phase diagrams. So as I told earlier, phase diagrams are graphical representations of what phases are present in a material such as at various temperatures, pressures, and compositions. So some of the important information obtained from a phase diagram is to show what phases are present at different composition and temperature under slow cooling, that is equilibrium conditions. So you know what is an equilibrium conditions. Equilibrium condition is nothing but the cooling of a material takes place. We are assuming that the cooling takes place at a constant temperature. When we are cooling, when we are heating a metal up to its melting point, and if we are cooling means then we are assuming that the cooling takes place at constant temperature. That is called as an equilibrium condition. To indicate the equilibrium solid solubility of one element or a compound in another, conditions of temperature and pressure. You can see this. There are two important points you have to notice down here. The point B, you can see this one is the point B. Point B represents the only combination of the temperature, that is 0.0098 degrees centigrade. At 0.0098 degrees centigrade and the pressure of 4.58 torr, where solid, liquid, and vapor phases of water coexist. Okay, this is the only point at which water exists in all three phases. Okay, it will be exist in water, solid, liquid, and vapor phases. Okay, so this is called as a triple point. It is therefore called as a triple point in the phase diagram in which all three states are in equilibrium conditions. If you see at pressure below 4.8 torr, water will present as either in the form of a gas Okay, you can see the phase diagrams can be classified into one phase diagram we have discussed, that is called as an isomorphous phase diagram, where two metals are completely soluble in both solid and the liquid state. Okay, then there is another diagram which is called as an eutectic diagram. The eutectic phase diagram can be classified into two states: two metals completely soluble in the solid state, completely insoluble in the liquid state, that is full eutectic. We call it as a full eutectic. Whereas two metals are completely soluble in the solid state, but partially soluble in the solid state, partially soluble in the solid state. Okay, so this diagram is called as a partial eutectic. Okay, so the equation governing this partial eutectic or eutectic phase diagram is: liquid, when it is cooled, it gives two different solids. Okay, liquid on cooling will give two different solids, that is alpha plus beta. Okay, or A plus B. Okay, alloy A and alloy B, metal A and metal B. Okay, two solid structure, you can get a lamellar structure of alternative layers of alpha and beta. Okay, then there is another phase diagram called as an eutectoid phase diagram. Okay, so the conditions, the governing equation is: a solid, when it is cooled, okay, it gives two new solids. Okay, when alpha, it is in a solid state, when it is cooled, then it separates, okay, into two different solid phases, that is beta plus gamma. Okay, there is another phase diagram called as a peritectic phase diagram, where a solid plus a liquid state, when cooling, will give a new solid beta. Okay, peritectoid, alpha plus beta, that is two solids, when two solids are cooled, then they give a new solid called as a gamma. Okay, and there is also another diagram, phase diagram called as a monotectic, which will not mostly consider. Okay, liquid on cooling will give alpha, that is a solid plus another liquid. Okay, these are the different types of phase diagrams available. You can see eutectic phase diagram, as I told. Okay, this is a condition where two metals are completely soluble in the solid state, liquid state, partially soluble in the solid state. In this kind of diagrams, okay, in the fully eutectic diagram, okay, you can see this point. From this point, directly this will come and touch the zero point. Okay, like this. In this side, from this point, it will directly come and touch the bottom. Okay, but when it is partially soluble in the solid state, the diagram will be like this one. Okay, it will be coming in the vertically. Okay, instead of touching the 0 point, it will come straight. Okay, so based on the amount of solubility of A in B or B in A, or amount of solubility in alpha in beta or beta in alpha. Okay, right. So for example, if you are taking a gold and a copper, okay, gold will dissolve only 10% of copper, but copper will dissolve 20% of gold. Okay, so in this case, this line will be touching the composition of 10%, and this will be touching the composition of 20%, like that. Okay, right. Now you can see there are several lines. We know this line is called as a liquidus line. Okay, this line is called as a liquidus line, above which the metal will be completely in the liquid state. Okay, so you can see this is a solidus line. Okay, center line is called as a solidus line, right, below which the metal will be completely in the form of a solid state. Okay, so and you can see another line which is called as a solvus line. Okay, this is a solvus line, because the metal A will be dissolving in B and B will be dissolving in A. Okay, right. So in order to explain this diagram, okay, we have to draw a vertical line at any point. Okay, so at the point A, it will be 100% liquid. Okay, as the time passes, the temperature goes on decreasing until it touches a point B. Okay, before which after which the crystals of alpha starts to solidify from the liquid. Okay, crystals of alpha will start to solidify from the liquid. Okay, so it continues, right. You can see the point B, right, and point C. Okay, so point C, you can see the solidification of the alpha from the liquid. You can see 76% of liquid and alpha is 26. The crystals of alpha starts to solidify from the liquid until it reaches the point D, below which the complete crystallization of alpha takes place. Okay, right. There is a point called as an eutectic point. Okay, so where there is only two states of matter, that is either it is a liquid state or it is a solid state, because you cannot see any solid or liquid phases, liquid and solid phases together. Okay, so you can go for an alloy one, you can see up to this point, up to the point that is nearly 200 degrees centigrade, okay, it will be completely liquid. Okay, below 200 degrees centigrade, it will form a alternative layers of, that is it will form a eutectic phase. Okay, that is solid crystals of alpha, alternative layers of alpha and beta will be solidified. Okay, you can see the final structure will be like this one. Okay, so alpha beta like that, it will be solidified. Okay, so you can see that, sorry, this one, the top eutectic alpha and eutectic beta will be there. Okay, right. So next one, the iron carbon phase diagram. Okay, I am not going to explain all these things, already these things are just basics. Okay, so iron carbon diagram, by combining different types of phase diagrams, we can explain the iron carbon equilibrium diagram. Okay, iron carbon equilibrium diagram is a diagram, okay, which is drawn between a temperature and the percentage composition of carbon. Okay, so the maximum solubility of carbon in iron is 6.67 percentage. Okay, so here you have to note down several points, okay, in the x-axis. Okay, so you have to remember 2 percentage, 4.3 percentage and 6.7 percentage. Okay, so you know what is 2 percentage of carbon. If the iron has 2 percentage of carbon, okay, up to 2 percentage of carbon, it is called as steel. The iron is called as a steel. Okay, so more than 2 percentage, if the carbon content is more than 2 percentage in iron, then it is called as a cast iron. Okay, so this iron carbon diagram can be classified into two parts. One, the up to a carbon content of 2 percentage is called as a steel, up to from 2 to 6.7 percentage it is called as a cast iron. Okay, still the steel region can be classified into 2. Okay, so that is up to 0.8, this one is 0.8, from 0 to 0.8 percentage it is called as hypoeutectoid. Okay, hypoeutectoid steel. Okay, if it is, if the carbon content is from 0.8 to 2 percentage, it is hypereutectoid. Okay, why we are calling this eutectoid means because here a eutectoid transformation takes place, that is a solid will give two new solids. Okay, already we have discussed that in the previous slides. A solid will give two new solids here, so it is called as an eutectoid phase transformation. Since eutectoid phase transformation takes place here, we call this region as a eutectoid region. Okay, so since steel comes under this category from 0 to 2% of carbon, we are classifying this as a hypoeutectoid steel and hypereutectoid steel. Okay, so coming to this region from 2 to 6.67 percentage, this is a cast iron region, because if the carbon content is more than 2 percentage in iron, it is called as a cast iron. Okay, so from 2 to 4.3 percentage of carbon, it is called as an hypoeutectic cast iron, because here a phase transformation takes place, it is called as an eutectic phase transformation. You can see, you know what is eutectic. Okay, either above the eutectic point, it will be completely in the liquid state. Below the eutectic point, it will be completely having a lamellar structure, alternative layers of alpha and beta, or A and B. Okay, so it is called as a eutectic region. Okay, you can see this from 2 to 4.3 percentage, it is called as an eutectic cast iron, hypoeutectic cast iron. Okay, from 4 to 6.7, you know what is hypertension. Hypertension means you will the carbon content is more, the material will be very much brittle. Okay, so they are called as an hypoeutectic cast iron. Okay, this is what you have to keep in mind in the x-axis. The y-axis you have to keep in different types of temperature regions, that is up to 727 degrees centigrade, it is a recrystallization. Okay, lower recrystallization point, 9-10 degrees centigrade upper recrystallization temperature. Okay, these 2 points you have to note it down. Okay, so then you have to note down 1400 degrees centigrade, 1493 degrees centigrade and 1538 degrees centigrade. Okay, so the melting point of iron is 1538 degrees centigrade, above which it will be completely liquid. Okay, so and also iron has a beautiful characteristics. Okay, so it exists in 3 different structures at 3 different temperatures. Okay, that's what it is called as a, what can you, it is called as polymorphism. The process when ion exists in more than one structure at different temperature, it is called as a polymorphic material. Okay, if this changes are reversible when we are cooling, then it is called as allotropic. Okay, so the same thing happens when we are cooling this metal. The same type of structural transformation will takes place again during cooling also. Okay, so at low temperature, that is from 0 to 912 degrees centigrade, okay, the ion will exhibit a structure called as an alpha ion. Okay, that is ferrite structure. We will get a ferrite structure here. Okay, it is called as an alpha ion. Okay, from above 912 degrees centigrade, okay, this structure, that is alpha ion, that is a ferrite structure, it is called as a BCC. It has a BCC structure, body centered cubic structure. Okay, so above 910 degrees centigrade, it changes its structure from alpha to gamma. Okay, that is the metallurgical name is austenitic structure. Okay, and it is having an FCC, face centered cubic structure. Okay, so above 400 degrees centigrade, once again this austenite structure, gamma austenite, will be transformed into delta ferrite. Okay, delta ferrite, once again it will changes into BCC structure. Okay, so this is iron is a peculiar material which exists in three different structure at three different temperature. So this type of transformation is called as a polymorphic process. Okay, polymorphism. Okay, if this change is reversible when we are cooling, okay, so where delta structure changes to gamma structure, okay, that is FCC into BCC, once again this gamma austenite will changes into alpha ferrite, that is once again BCC structure at low temperature. Okay, this process called as an allotropic process. Okay, so this is what you have to understand from this iron carbon equilibrium diagram. Okay, so in addition to these things, you have to note down three different phase transformation takes place. One, it is peritectoid reaction, eutectoid reaction, and eutectic transformation. Three different transformation. Okay, at the top, peritectoid reaction will takes place. At the bottom on the left hand side, you can see a phase transformation, that is an eutectoid phase transformation, because already one solid is formed. Okay, so this becomes eutectoid now. Okay, but if you go to the right hand side, you can see only an eutectic phase transformation will takes place on the right hand side. Okay, so the three different types of phases. Okay, and coming to the microstructure, already I have told you a ferrite structure, an austenite structure, and delta ferrite structure will be there. If you come on to the right hand side, okay, so at the leftmost side, you can see a ferrite structure. Okay, as the carbon composition increases, okay, this ferrite structure changes into pearlite. The ferrite structure changes to pearlitic structure. Okay, so as then when the carbon content goes on increases, this pearlite structure changes into a ladyburite structure. Okay, ladyburite structure. Then as the carbon content goes beyond 3%, okay, the ladyburite structure can change to sorbite structure. Then it changes into a cementite structure, which is a hard compound. Okay, hard compound, which is called as an Fe3C. Okay, Fe3C, pure Fe3C, it is called as cementite structure. So since some amount of alpha is present with the Fe3C, it is called as a pearlite structure. Okay, so pearlite structure, right? At 727 degrees centigrade, okay, above 720 degrees centigrade, this austenite structure is unstable below this temperature, 720 centigrade. So the ferrite structure will not be available above 727 degrees centigrade. It will change into austenite structure. Okay, austenite structure is unstable below 727 degrees centigrade. So it is a high temperature structure. Austenite is a high temperature structure. You can see in this region you will be having gamma, that is austenite plus iron carbide. That is iron carbide is nothing but cementite. Austenite plus cementite structure. Above this point, in the right hand side, you can see you will be having a completely liquid states. Okay, these are the informations we can obtain from a iron carbon equilibrium diagram. Okay. Right, you can see this is an eutectoid transformation. This is a diagram which represents the eutectoid phase transformation. Okay, already you know what is an eutectoid phase transformation, where a solid, that is gamma austenite, will changes into two new solids, that is alpha plus Fe3C. Austenite is, already I told, austenite is unstable below 723 degree, 723 or 727, that is the lower recrystallisation temperature, below which it transforms into alpha plus Fe3C structure. Okay, see here in this, at this point it will be having a pearlitic structure. If the carbon content is more, it will changes into a cementite structure. But since you can see, this is the eutectoid region where it is having a less than 2% of carbon. Okay, so it will be having a structure called as a pearlite structure. Okay, right. So this is the how the transformation takes place. This is a diagram which on the right hand side, this is a diagram which explains how the transformation of gamma into alpha plus Fe3C takes place at various points and stages. Okay, right. So this is the microstructural representation of a hypoeutectic plain carbon steel. What is a plain carbon steel? Plain carbon steel is a steel which is having a carbon content less than 0.3%. Okay, less than 0.3%. Generally these steels are called as a mild steel, which we are using mostly in our applications. Okay, nowadays all the ions we are iron material we are using is called as a mild steel material, where which has a very low carbon content in it. Okay, the 0.4% of carbon. Hypothetical steel heated above 910 degrees for sufficient time, structure will become homogeneous austenite. Then if the steel is slowly cooled to a temperature about 775 degrees centigrade, the ferrite will nucleate and grow mostly at the austenite grain boundaries. If this alloy is slowly cooled, the amount of pro-eutectoid ferrite formed will continue to increase. While the steel is cooling, the carbon content of the remaining austenite will be increased from 0.4 to 0.8 at 720 degrees centigrade. If very slow cooling conditions prevail, the remaining austenite will transform isothermally into pearlite by the eutectate region. That is what we have discussed in the seen in the previous diagram, and you can see the microstructure. Okay, so in the hypoeutectoid region, you can see the microstructure of the pearlite. Okay, the black spots are called as pearlite. Okay, the white is the austenite. Okay, this is not homogeneous, so you can see the eutectoid structure is a homogeneous mixture. Okay, homogeneous mixture, which is you can see the ferrite and the pearlite structures will be present in this one. Okay, right. So these are the diagram which represent the hypoeutectoid plain carbon steel. Okay, so with this we will end this session. The next topic we are going to discuss about the non-equilibrium phases in the